you have a sample, one sample, and okay. Wow,
Now it's
that's very
okay.
powerful voice now. Okay, so imagine that you have this one sample and you measure pH. This is one variable, okay? But we normally don't have this scenario. We normally have many samples, and actually in those many samples we don't normally measure only one variable. We measure several variables. So imagine the structure in which we have sites, we have samples here, and then here we measure several variables like pH, concentration, temperature. Then if we add, for instance, another dimension like seasonality here or campaigns, we can actually arrive to have one three-way structure like this one, okay? Then, if we move to first order instruments, like for one sample, we have the spectrum at a certain time, or at one sample, we have a vector, we have a spectrum. But actually, if we monitor this reaction, for instance, at more times, we have many spectra. So basically, we have our matrix here of one experiment, okay? In the sense that here we will have time, and here we have wavelengths. So we have our matrix, right? But what happens if we have more samples than one? Because not only we will have the rows, that is the time, the columns, that is the variables, okay? But actually we will have an extra dimension that could be the dimension of samples, okay? And let's say that the highest applicability of these methods comes in secondary instruments, like for instance in gas chromatography or liquid chromatography when it's coupled to a sensor that is able to collect different wavelengths or different mass fragments. For instance, like in this example that you have here, in which we have the elution time here and the wavelengths for the detector. So in each elution time, we have one vector that is again our matrix. And if we collect more samples than one, we have our structure here. Or also we have instruments like fluorescence, excitation, emission fluorescence, in which we can collect for each excitation wavelength, we can measure the emission spectrum here. So for one sample, we will have our matrix, and then if we have more samples, we will have our three-way structure. So then actually, if you revise in the literature, you will find many examples, for instance, in sensory analysis, process analysis, image analysis, experimental design, spectroscopy, or even environmental analysis in which you can find these three-way structures, okay? So actually, one of the classic ways of dealing with this data was to unfold our three-way structure in the sense that, for instance, here for each measurement that we have here time, we can unfold in the sense that we have each spectrum one after the other one, okay? So we can do the same with different samples. And at the end, what we will have is an augmented matrix, okay? So if you think about this structure, there are actually three ways of unfolding this matrix. So sorry, this three-way structure. So for instance, here we have wavelength sample pH. We can create a matrix that is sample times wavelength pH, or pH times sample wavelength, or wavelength pH type samples. So at the end, this complicates a little bit the story. Okay, so instead of using these approaches for many years, there have been approaches that deal with this three-way array directly. Okay, because unfolding a part of breaking the nature behavior of the data, it also leads, so in certain cases, to overfitting of your models. Okay, so actually, this is not new. Okay, it was proposed already in 1944. Okay, something called parallel proportions. Oh, by the way, if you see numbers here, don't worry, because this makes reference to the list of references that I have at the end of the presentation. Okay, so you will have this corresponds to the reference number 5. So you have these parallel proportions in 1944 that was revisited and defined in 1970 by Robert Harsman, okay, and he defined it like parafac. parallel factor analysis. Okay, and at the same time, there was Carroll and Chan defining it as canonical decomposition. Okay, but we generally know it as parallel factor analysis. And what these methods do? Okay, before that, I have to say that actually from this point, we arrived to the great professor Bruce Kowalski and the great professor Svante Vold. And actually, in the 80s and 90s, they started defining different models like GRAM, generalized RAM annihilation method, or trilinear decomposition, or PLS, that's familiar with you, probably with residual bilinearization. Okay, so these are variations of the different algorithms that you can apply for three-way analysis, and of course, from this group, we can actually highlight two branches. Okay, this is very fast, but two main branches. The branch that is still kept the three-way structure, that is the one we are going to talk about today now. Okay, like that Professor Pro, Smilde, Yeladi, or Nikos Iliopoulos with Parafac, Parafac2, MPLS, Parafasca, etc., or the branch that decided to make some folding in specific conditions and start applying multi-brave curve resolution methods that you have heard before, a really great presentation. Okay, and there is also this branch here that I will not talk about, where Alejandro Olivieri is very expert in using this residual bilinearization in the PLS model. Okay, so basically, to put it into framework, PCA and MCR, okay, they are both bilinear models. They basically, what they do is to factorize this matrix and subdivide the matrix into the product of two submatrices, scores and loadings. Both of them do it in a very different way. PCA, you already know that PCA does it applying orthogonality in the principal components. MCR is a more free model, and we use another constraints like non-negativity, unimodality, etc., etc. Okay, so actually the three-way methods, and let's focus on Parafac, parallel factor analysis. Parallel factor analysis. That's not the same, okay, but graphically speaking, it can be assimilated if we understand that instead of dividing this three-way structure or this matrix into two, now that we have a three-way structure, we will divide it in the or the product of three submatrices, okay, with special conditions, of course, depending on the algorithm. But let's say that this decomposition Parafac will decompose the three-way array into the subproduct of these three matrices that we will call scores of A, scores of B, and scores of C. Okay. Then there are some different crucial differences to consider, in the sense that I think it's better to do it with an example. If you remember before the presentation of multi-brave curve resolution, actually Parafac could be considered as an extension of multi-brave curve resolution in a three-way perspective. So if we have here the excitation emission samples, and this is for one sample, and here we have many samples, what we are going to do is to factorize, is to divide this three-way array into the product of these three submatrices: the excitation loadings, okay, the emission loadings that comes here, and also we will be able to obtain a score here related to the components that we have just obtained. Okay, so this is basically what we are going to do with these three-way structures. And the main features for this model to work, okay, this Parafac model, is that okay, the components now, they are not constrained to be orthogonal as we do in Parafac, as we do in PCA, and the data needs to be trilinear. Okay, and this trilinearity is a concept that we will see later in an example that is very clear, actually, what it means to be trilinear. Okay, and of course, it's a curve resolution method, so we have the second order property. Okay, That means that our answers under the certain constraints is unique, so we can solve the mixture of analytes, okay? We can estimate something called relative concentrations. They are not absolute concentrations, but relative concentrations. That means these scores, okay? And we can also estimate the pure spectral profiles, but now in two dimensions, differently to MCR that we only have one dimension, okay? So an example, this is just real examples, okay? This is a collection of samples of vinegar, Spanish vinegar, okay? And we measure excitation emission with the aim of differentiating the vinegars, okay? We have different categories. So what we did at the end is to measure each vinegar independently, okay? This is excitation emission, and for those who are familiar with excitation emission, you know that we have to remove any Rayleigh and Raman scattering effect because they are clearly nonlinear in these cases. So what we do is to collect all this data and to generate our three-way array. So the first thing we have to do in this type of methods is to obtain the proper number of components. And in Parafac, we have, of course, the explained variance, but we also have something called core consistency. The core consistency is it's a mathematical parameter that tells us how trilinear or how good our data fits to a trilinear model, okay? So actually in this case, we can see that with an unconstrained model, because we apply constraints that comes also from MCR paradigm, like non-negativity, unimodality, etc., in an unconstrained model, 4 would be probably the most suitable model. But then if we apply non-negativity, we can go up to 5, okay? Because we also know that applying this type of constraints stabilized a lot the models. So basically, when we apply Parafact to this data and we do it with, uh, with those constraints, if you look at this model, that is the proper one, we can extract up to 5 components that are extremely overlapped. Let me show you data again. This is the data, okay? So the good thing is that we can extract up to 5 components, okay? And not only that, we can check if those components they have chemical meaning. Of course, they do have chemical meaning, but also with the scores, what we can do with this third mode, what we can do is to represent them as we do it with PCA. Same, this is factor 1 against factor 2, and we can differentiate those vinegars due to the different, for instance, in this case, due to the different aging of the vinegars, okay? But we can profit some other properties of these three-way models, that is the adaptation of them to a quantitation or prediction paradigm, that it would be what is called NPLS, that is a regression, okay, using properties of PLS, but in a three-way manner. And here we have an example in which what we do is um, to generate biomass from a bioreactor. Okay, so basically what we did here is to monitor the development of 3 amino acids that are quite common in biomass production, like tryptophan, NADH, and riboflavin. Okay, and we want to correlate this with biomass and the production of lipase. The thing is that what we proposed is this is the bioreactor, okay, and then we plug this probe that is able to measure the excitation emission. And in parallel, what we did is to extract a liquids, okay, and measure the depletion of methanol, because methanol is the food, okay, in order to generate this biomass. So we did it because we wanted to propose that instead of making invasion in this reactor, that is introducing a probe in order to extract a sample so we can measure the methanol, we can directly measure the excitation emission from here, okay, and obtain these maps for each sample at different times. And we don't need to open the reactor, so we don't compromise the sterility of the reactor. So actually, this is the signal evolving with time. So as you can see, 2, 4, 6, 8, 10, up to 14 hours. You can see that there are things happening here. And then all these samples for each time we collected in our three-way array, in our matrix, in a three-way structure in which in this direction we have time. Okay. So actually, applying Parafat, what we expect to obtain is the two excitation and emission loading profiles of the compounds emitting fluorescence at specific wavelengths, and also an estimation of the relative concentration. And in this case, since this is a closed system, what we expect to see here in the relative concentrations is the evolution, direct evolution of these three compounds at the same time, okay? And of course, some residuals. So look at this. These are the results. In here, we will have time. And this is actually, this is wrong. This should be a score value, okay? And this is what happens with the tryptophan, okay? We obtain this spectra, and of course, we could compare with databases to really assess that this is the tryptophan and look at the evolution of tryptophan. That is very beautiful. So it arrives a point in which we stop having more signal of tryptophan, okay? Then this is the NADH, and basically it occurred the same. And this is what happened with riboflavin. With riboflavin, we were not able to see a stopping point. But what is more important to this is that we could actually see the different periods that happens in a biomass generation, okay, that setting that this is the stopping point, and this is what happens with the offline measurement, that is taking some liquids. We could clearly see that at this point, then we stop seeing the more signal coming from the tryptophan is when there is no more methanol in the reaction. That means that here we have arrived to our stopping point, so stopping criteria, so we can start a new batch, okay? So actually another thing that we could do with this is using the residuals of the model, of the Parafat model. Actually what we can do is to establish control limits. So we go to not a multivariate statistic process control, but a multi-way statistics process control. So with these residuals, we establish different limits. So this limit is actually a warning control, and this is actually a very precaution control. So there is something out of control, okay? In that regard, when we measure in the next batch for one sample, we can actually use the loadings that we have obtained in the previous in the calibration model, just because we have the second order property that is we can use this information regardless having other constituents in our samples, and we can calculate a score value that we can project in that graph that we have seen before, and we can do this with time, so we can detect actually if our batch, if our process is under controlled conditions or not. Okay, so look what happened, because this is actually what we wanted to do, and this is the actual control chart that we implemented. And here in the top, you will see the loading values of predicted of a predicted batch. Okay, and here you will see the residuals. And actually, it's really nice because we can define, we can predict at real time what's going on in there. Okay, and indeed, if we want to extrapolate this to real, because this was in the laboratory, to real industry, in Denmark, there is a company that controls the development of biomass and of sugar production, okay, by using excitation emission fluorescence. And I can show you the results in which here we have days, okay, and you can see how the blue line matches the brown dots. The brown dots are the offline measurements, and the blue line is the real-time measurements. And not only that, they are actually able to extract the information, the chemical information of what's going on those processes. Okay. Another field in which three-way analysis can be used a lot is in chromatography. Okay, in which part of the chromatography? Well, in the part in which for each elution time we can record a full spectrum. In this case, it's a mass spectrum. Okay, so we can have this signal that is the chromatographic signal, but for each elution time we have one spectrum. Okay, so this is basically what we have at the end. And if we have more samples, we can arrange our three-way array. So if we use Parafac in order to define these chromatographic dissolution profiles, what we will find is that Parafac is really good at giving me the resolved elution profiles of the components together with the pure mass spectrum. So we can go to libraries and check if this works. And we can see with the integrated signal here, that is with the score, we can actually project them as we do in PCA, score 1 against score 2, and see if we have any evolution or any differentiation in the samples. But there is a problem, like always in life, there are always problems. Three-way methods, especially Parafac, only works, as I said before, when the data is strongly trilinear. Okay? What is non-trilinear data? Because I think it's easier to understand what is non-trilinear data if we see it with an example. This is a picture. As you probably know, pictures are made. One of the ways of making pictures is to collect the RGB channel, right? So if we collect these RGB channels and we have this beautiful picture in which I am with Rasmus. First time I met Rasmus, 2005, in his office, okay? But what happens if now I move the green channel a little bit to the right? What happens is that we see the picture blurring, right? So basically, in every pixel here, we have correspondence, a spatial correspondence for each pixel here. But if we move this channel to the right, now we don't have a spatial correspondence. Okay, so basically for these two dimensions, we have lost the correspondence in this third dimension. Okay, so if we translate this into chromatographic data, this is the perfect chromatographic data in which every peak coelutes at the same, each component coelutes in all the samples at the same elution time, but this is not real. Normally we have this, we have elution time shifts. So basically this is the same that happens here, and this is one of the reasons when we lose trilinearity. There is no any more correspondence between this dimension and this dimension with the third dimension. Okay? If we extrapolate this example to excitation emission profiles, it is exactly the same case. Okay? But in chromatography, it's more normal to have these situations of losing trilinearity. And actually, there are many reasons in chromatography in which we can lose trilinearity. Like, for example, we can have elution time shifts, we can have baseline drifts, and we can have low signal-to-noise ratios that promotes more problems with baseline solution, etc., etc. Moreover, those problems do not appear separately. So what normally we have is this one. This is real life. Okay. So when we have a case like this one, Parafac cannot handle this problem properly, or it's very difficult to have a good Parafac model. So there are two plausible solutions. Okay. The first solution could be the alignment of this data and using Parafac. That is not advisable because we might have other problems in the action, or sorry, in the chromatograms, or we can actually generate many problems when we align the data, because alignment of chromatographic peaks, as you probably know, is quite complicated sometimes. But there is a second option, that is using a variation of Parafac that is called Parafac 2. And actually, since now we are talking about three-way analysis, I will talk about Parafact 2. But later, I think I have to talk about MCR applications. So I will show you also how to use MCR in this type of data. But let's talk about Parafact 2 because also Rasmus is one of the ones that I think he would love to use Parafact 2. Okay, because he was actually the one proposing Parafact 2. So what is Parafact 2? Okay, Parafact 2, it's analogous to Parafact. Okay, we follow the same model except in one thing. Now we have one of the modes, one of the loadings. Okay, in this case, our loading will be the illusion profile in which it moves from sample to sample. So Parafact 2 is able to decompose this three-way array into the product of these three submatrices, but allowing that for each sample here, we can calculate one specific illusion profile. Okay, so in that sense, in that regards, the problems that may arise in your chromatographic data that they are reflected in the illusion profiles will be minimized or even solved because we will allow this mode to be more free than modeling only one of the profiles. Okay, and what we will obtain, as I said, is in Parafact, we have our matrix of our vectors of scores and these two loadings. But in Parafact 2, we will have the same matrix of scores. And for the spectra, we will have also the same spectra. But for each sample, we will have a different illusion profile. And that is wonderful because it makes possible to apply three linear models in chromatographic data, as this example shows, in which this is Danish apples, and Danish apples are used in Denmark for many recipes. They are very traditional and they are very intense and characteristic aroma. Okay, but there is a problem with these apples is that they don't know when is the perfect ripening period. That is, it has to be really precise, this ripening period, because we want the apples to arrive to the customer, to us, with the highest aroma possible. Okay, so what we did is to take some apples and to submit them to different ripening times, and then we measure the aroma chromatographic profile. We use GCMS for doing that. Okay, and the thing is that when someone sees this data, we trend only to analyze the major components. Okay, but here in aroma, minor components are extremely important because they are actually can have a powerful aroma. Okay, so it is extremely important here to analyze also these minor components. Okay, but what happens with these minor components is that sometimes it's difficult to integrate them, to see them. So we can have peak shifting problems. Okay, we will have low signal to noise ratio problems, and also we will have baseline problems. And in some cases, we will even have severe overlapping of the data. So basically, what we decided to do is to cut this chromatogram into, I think, 26 different blocks and apply Parafact 2 models on those 26 blocks. How did we do this chopping? Well, we did it considering what aroma experts told us where we could find the most important components here. Okay, so I will not show you, obviously, these 26 chops, but let me show you some of the ones that we could clearly see that Parafact 2 made a really nice job. For instance, in this interval, we were able to quantify 5 compounds. Okay, and actually, the good thing of using mass spectrometry is that after that, you can go and check those spectra in libraries, so you can have your assessment there. that the decomposition has been done correctly. Look at this case. In this case, I always like to show it because now is the time I ask you how many components can you see here. Okay, and probably there you are thinking one, maybe since this is a presentation and I want to show off a little bit, two or three. Look at this. We took parafact 2 and we did analysis here, and we were able to find up to 1, that is the green, 2, that is the red, 3, that is the tail of a previous compound, and 4, that is the baseline, actually. So we were able to measure or to model the baseline. We were able to unravel this strong, severe overlapping, and we were able to actually see that when we cut the intervals, we need to be careful where we cut, but if we are not that careful, there is no problem because we have this tail of the previous peak, and what we can do is to remove that tail because here basically we didn't obtain the full peak. So 1, 2, and 3 elements, 3 components that were actually helpful, and they were identified actually, okay? Or even in this case, there is an extreme overlapping case in which we were able to find 1, 2, 3, 4 components in here overlapped. Okay. So with these results, what we did is to take the scores, the same scores that it could happen in parafact. It happens in parafact 2. We took those scores, and with those scores, the scores of each peak of the 26 intervals, we were able to detect more than 50 compounds, and not only that, we were able to see the differences between the different days in which the apples were ripened, like between 5, 8, and 15 days, and there was this evolution in the scores, okay? And look what happened here, because it's really nice to see that this evolution corresponds to different molecules that have been created while the apples are being ripened. So basically, they are growing in ethanol, propanol, butanol, pentanol alcohols, okay, and other elements that are more heavy, like esters and things like that. They are actually only in the 5 and 8 days. So with parafact 2, we were not only able to see to see this evolution, but what it catches the attention of everybody is that we compare this example with what a chromatographist, a normal chromatographist would do. That is to take these samples and to integrate manually peak by peak. Okay, with any luck, there might be some software in the instrument to solve the overlapping things. The thing is that that person was able to find 35 compounds. We were able to find more than 50. And the thing is that we were able to do this in one night, while the other person was 2 weeks integrating peaks. Okay, so actually, it was a huge improvement in here. Okay. And to conclude, I want to show you a couple of examples in which I think the movement and the current science is moving forward. That is, one of them is data fusion. Of course, for one sample that we have here, for one sample nowadays, we have the capability on our laboratories to measure that sample with different spectroscopic or chromatographic techniques, like in this case, in which we have LCMS, integrated peaks, together with EM, excitation emission fluorescence, together with NMR. Okay, so actually we can fuse all this data in order to first see the commonalities between the different blocks, and second, check whether that fusion helps to our target, that in this case was classification. So let's come back to the vinegars story, because we not only measure with parafact those vinegars, we measure them with middle infrared, near infrared, and also NMR. So clearly here we have three matrices and one three-way array. Okay, so we can fuse them, we can fuse all this information in order to classify the different categories in the vinegar. And with data fusion methods, in this case we use peak on dim, we could actually see what is the influence of the excitation emission factors compared with near infrared and middle infrared and NMR. And actually doing this data fusion, our classification actually improved. Here we are in the test. Here improved quite a lot from the classifications done with the individual data sets. Okay, and a glimpse on how this is evolving. Of course, nowadays there are more and more algorithms in the literature. I especially like one of them that is paralinked, parallel profiles with linear dependencies. That means that there may be situations, if we think about chromatography, in which we can have several compounds coeluting, but for any reason, two of those compounds might share the mass spectrum. Okay, how come this is possible? Okay, so let me just put you an example. This is a real example in which we have samples, okay, that has been derivatized, and here we have two peaks, okay. So actually, our first intuition was to use, okay, peak alignment together with Parafag or Parafag 2 or even multivariate Q resolution models, okay, because we wanted to obtain these three, but it was impossible to obtain a good model with these three eluted compounds. So we decided to use MCR. The best model that we obtain is with four components. So as you can see, the resolution is not really good. And we didn't know why, because we clearly see here two peaks, okay? This is the best Parafag 2 model with four components. It was a disaster as well. So actually, we realized that we had a problem with these two peaks, okay? At the beginning, we thought that they were isomers, so that's why they had the same mass spectrum, but it was not that the problem. The problem was that these two peaks actually, it is the same molecule, but due to the derivatization problem in chromatography or derivatization stage in chromatography, what happened is that the same molecule had different kinetic reactions to the derivatization process. So these two peaks are actually the same molecule being derivatized at different times, okay, at different reaction times. So actually we thought, okay, so if these two fellas are the same molecule, why don't we constrain these two to have the same spectrum? Okay, and in this case, we can actually model the elution profile and the concentration profile of both of them independently, but constrained to have the same spectrum. And what about the third compound, this compound here? Okay, so we can leave it to have their own elution profile, their own concentration, and their own spectrum. So when we apply this paradigm that is called paralint, that is what it stands for, parallel profiles with linear dependencies, and this is a dependency, we were able to find this model that is incredible because we still have the baseline around. We have the profile for one of the peaks. We have the profile of the other peak, independent, and then we could actually model our tail here coming from other peak. Okay, so with this, I want to say that there are already many libraries, mostly in MATLAB, but there are also in Python and R, in which you can use these methodologies, but also, especially in the group of chemometrics in Copenhagen, at the University of Copenhagen, they have been specialized in creating toolboxes in order to make our life easier. Like, for instance, eMiser, that is an automatic way of doing Parafag on excitation emission fluorescence. Scream, that was published by Rasmus and Federico Marini, probably you all know him. That is Parafag DOS for quantification. And Paradise, that I was lucky to work a little bit on this project, but Paradise is a full automatic Parafag 2 solver for chromatographic data, GCMS mostly. Also about the speed, there are new advances in which the problem of Parafag 2 mostly was the speed. It was very slow in computation, but it seems that last year Rasmus and other people solved that problem. So you can check in the literature because now doing Parafact 2 is way faster, but I don't have the experience now. Um, Reliability and model optimization. We still are working in how to optimize the models. How can we really validate these models? Okay. And especially about the implementation in commercial softwares, because there are more and more commercial softwares in which you can find all this software already implemented. I think as far as I know, that there are a couple of instruments of excitation emission fluorescence that they already have Parafac by default, and I think that some of the chromatographic instruments they are starting to implement some things similar to mostly MCR, but also Parafac 2. With that, I also want to highlight that if you look at the bibliography, there are more and more of these type of algorithms being created nowadays. I just saw you Paralind because, well, first of all, because I used it, and I only talk about what I use or what I understand. But there are many other options in the literature, like something called Parafasca, for instance, in which you can use ASCA paradigm in Parafac type of models. Okay. And also, with this, I want to conclude this talk. But if you want, Hadi, I can send you the presentation in PDF, so you can have the main references for if you want to master in multi-way analysis. That is mostly these two books, okay, multi-way analysis by Age, Rasmus, and Paul, and also the PhD thesis by Rasmus. And in the literature, there are many of them, many books. And also, this non-negative matrix and tensor factorization is basically the same, if not well, very similar, but if not the same, in which this non-negative refers to the fact that we apply non-negativity constraint in the modes. And there are many references that you can check. Okay, so thank you very much.
Okay, thank you, Jose, for your nice and informative presentation. I think there are some questions from the participants. Any question? من خواب بودم. ببخشید چراغا رو روشن کردم. یه سوال حداقل بپرسید خیلی به نظرم. Okay, so I have a question regarding the application of Parafac and Parafac 2. Is there any threshold for the deviation from trilinearity in the data? Because in some cases you don't know that is it possible to apply Parafac to this type of data, or in other words, is there any test for checking the extent of deviation from trilinearity in the data?
Yeah, that's a good question, actually. And that's a question that I made to myself and to Rasmus many years ago. And still it is not solved, sadly. Okay, but after talking quite a lot with Rasmus and Romain about this topic, I can give you a hint. Here we are. There was an old rule, but I'm not really convinced of that rule that says that if you unfold this three-way array, if you unfold it in the three ways you can do it, different ways, and you apply PCA or singular value decomposition, and you obtain the same number of principal components that are significant, that's a hint of your data being trilinear. But I tried myself several times in different scenarios, and I was not really convinced. So it is really difficult to check when your data is non-trilinear. I would say that excitation emission, it has to be naturally trilinear. And I would say that chromatography, it's normally non-trilinear. Indeed, when it comes to chromatographic data analysis, I work a lot with Parafac 2, but I have to say that applying multivariate Q resolution approaches, it might be more home safe, so to say. So Regarding to your question, no, there is no a threshold that says this is trilinear, this is not trilinear, because not even the core consistency parameter, it's a kind of reliable parameter per se. But I would say that if something is deviated from linearity in excitation emission, I would be concerned that my device is not measuring well or that something is wrong with the acquisition of the data. And I would say that chromatographic data is 99% of the times non-trilinear.
Okay, because you know that Robert Sinovic in Seattle, they have an index for calculating the deviation from trilinearity, that is TDR.
Yeah,
Trilinear deviation ratio, that I don't remember how to calculate this TDR, but it's like an index for calculating the deviation from trilinearity in the data.
yeah, it's an index. I think they use the core consistency as a basis.
Yeah, yeah.
But I check it. I mean, it's a long time I don't work with trilinear models, huh? But I checked it a long time ago, and I was not really convinced either because I could find cases in which the data is clearly non-trilinear, but still that parameter gives you somehow good results. So
Okay.
yeah,
Okay, thank you again for your nice presentation. So we will back to you in around 1 hour because we have a 15 minutes break and then another talk, and then we will back to you.
perfect. So now is my lunch time.
Yeah,
Thank
okay.
you.
Bon appetit.
Merci.
Bye.
Bye.
خب دوستان، ما البته 20 دقیقه از برنامه عقبیم. برای همین دوستان پذیرایی رو آوردن جلوی سالن که دیگه خیلی پخش نشیم. تشریف برید برای پذیرایی و بعد بلافاصله برمیگردیم با سخنرانی آقای دکتر مانی در خدمتتون خواهیم. بفرمایید.